Now, in case you couldn't read my writing or you were lost or whatnot, I have the solution on the PowerPoint slide. But again, you got to do it on your own. So do it on your own and then check it with what I have here. So here's the two force diagrams, and here's all the math. And there you go. All right, so there you go. All right, this is kind of a neat one. It's not so much math. Yeah, by the way, let me say something about this one. What was so difficult about this one, or what was new about it? The only thing that was new is that B pushed on A and A pushed on B. That's the only thing that was new. I mean, other than that, it was just kind of like what I would call a robot problem, you know? It's just, you do your kinematics, you do your two force diagrams, and it's just math. Now, there's a lot of math, but still, I mean, there wasn't a whole lot that was new. I mean, but you had to use this, right? The magnitude FA on B equals magnitude FB on A. So you had to use that. All right, so a lot of math, but, you know. Okay, let's talk about this one. So everybody read it, or there's nothing to read. Okay. So first of all, we see our three-letter word that we love to see, ice. Remember, physics 121, ice means no friction. Yes. Okay. So this is kind of a cool problem because you can do it more than one way. All right, so it says, and look at the string doesn't have any mass. That's the second thing we like to see, right? Okay. So given T3, so look at what's T3 doing? T3 is pulling all three blocks, right? So T3 is doing all the work, right? So given T3 is 65 newtons, find the acceleration of the system. Now look, these ropes don't stretch or do anything weird. So what's going to be true about the acceleration of each block? The same, right? The same. Okay, so let's do it. All right. So again, T3 is pulling the whole mess. So in your head, or maybe on a piece of paper, this is what you should draw. You should just draw T3 is pulling 1 and 2 and 3. All right? Okay. So there's your force diagram, right? So the sum of the forces, there's only one, okay, all we care about is horizontal. We don't have to worry about the normal and the weight, right? So the sum of the x forces is T3. That equals m1 plus m2 plus m3a. So A is just equal to the force divided by the total mass, and bingo, you got that. Well, that's nice, right? Okay, so we know that A equals 0.97 meters per second squared. Okay, now, that was easy. But I mean, it's easy as long as you realize that T3 is pulling everything, so this is the correct way to draw it, you know, for T3, okay? That's the point. That's why I'm doing this problem, so you can see that. Okay, now we want to find T1. There's a couple ways of doing this, but I want you to do it the easiest. So what is T1 pulling? Well, I mean, T1 is pulling M1 to the right. On the other hand, T1 is pulling M2 this way, but T2 is pulling it that way. So, I mean, you have your choice. What do you want to be the object? If this is the object, if M1 is the object, what's the force diagram? Horizontal force diagram. Just that, right? Well, that's wonderful, you know? This would be M1. If M2 is the object, then we have T2 going that way and T1 going that way. Well, if we want to solve for T1, I mean, if we're going to use this one, then we have to know what T2 is, right? And we don't know what T2 is, so I don't want to do that. But this one, I mean, we know what A is. We know M. We can just solve for T1. So let's be lazy. What do you say? Let's be efficient, okay? So there it is. That's the force diagram for M1, right? The only horizontal force is T1. Okay, so piece of cake, right? So sum of the forces equals T1, and that's M1A. We know M1, we know A, we're done, okay? So T1, big deal, okay? So M1 is the object, just calculate T1 as shown. Well, that's nice. All right, now, T2. Well, what do you want to use for the object? It's up to you. If you use M2, what are the forces acting on M2? T2 that way, T1 that way. So we would just say that the sum of the forces, T2 minus T1 equals M2A. Piece of cake. That would be a reasonable thing, right? But you know what else? We could also, what if we use M3 as an object? Then we have T3 that way, which we know. We have T2 that way, which we want to find. We could do it that way. Either way would work, right? Either way would work. There's even a third way we could do it. What's T2 pulling? T2 is pulling this plus this, right? So we could actually do this. M1 plus M2 T2, right? We know what the acceleration is. We know what the masses are. You can do that. So there you go. 3 ways to do it. Pick whichever one you want, Okay, so I don't know why I chose that one. No good reason, So choose this for the object. So T2's that way, T1's that way. So the sum of the forces, T2 minus T1 equals M2A. So you just solve for T2, put that on the other side, you just do it. So there you go, all right? So that's kind of a nice problem, okay? So I wanted to do that problem just kind of to show you how important it is, which object you choose. Some choices will be good, some choices won't be so good. So that's a nice little problem. All right. Oh, you want to do that? Let's do a real messy one. What do you say? Yeah, let's do a messy one. Ooh. A 1 kilogram block is tied to the wall with a rope. All right, so this guy's not moving, right? This guy's not moving. It sits on top of a 2 kilogram block. The lower block is pulled to the right with a tension of 20 newtons. Then they give you the coefficients of friction. What is the tension in the rope holding the 1 kilogram block? Wow. Okay. This is the time you need to draw the force diagrams. And this is not trivial. This is a tough one. And you're going to have to use Newton's third law. All right, so pause your video and draw the force diagrams. Okay, we're back. I hope you've drawn the force diagrams. So what are the forces acting on this one? Well, there's weight. There's a normal force from this one. Now, there's friction, and there's tension. What are the forces acting on this? So there's friction here, there's tension here, there's normal here, there's normal here, and there's weight there. Whoa! Okay, so I think I have the pictures drawn. Yeah, phew, good. All right, so the top one. Okay, so there's the normal. Okay, I don't really like this. I would have said norm. So this is the top one, right? I would have said 2 on 1, whatever. But anyway, there's a normal, and again, be careful. This normal here is this normal, right? It's 2 on 1, Okay, so there's the normal, there's the rope. Now, why is there friction this direction? Well, again, this thing is moving to the right. Agree? This is stationary, this is moving to the right. So just pretend there's sandpaper up here, on both surfaces. As this moves to the right, isn't it trying to pull the top block to the right? Yeah, it is, right? So that's kind of a new thing, but I mean, if you think about it, it makes sense. So F1 is to the right, and then we have weight. No kidding. All right, now this is the complicated one. So, all right, so again, I would have said this is 2 on 1, so it has to have a 1 on 2, right? Right? If 2 is pushing up on 1, 1 is pushing down on 2. So we have an N1 here, we have an N1 there. You also have, okay, so this is being pulled, so we have friction opposing motion here, you have friction opposing motion here. So we have F2, this is friction top, this is friction bottom. You have weight, no kidding, right, weight. And you have the normal from the surface, N2. All right, woohoo! So that's pretty cool, right? So 1, 2, 3, 4, 5, 6 forces. 6 forces on that bottom one. That's incredible, right? Okay, so this is the key, right? If you don't have this drawn properly, you can't solve the problem. It's as simple as that. So, okay, now let's do it. So we'll do an easy one first. M1. Okay, so let's just be a little lazy, huh? It's not accelerating this way, so N1 equals M1G, right? Okay, so I'll do it. So the sum of the y forces equals 0, therefore N1 equals M1G. Okay, we also know that the sum of the x forces equals 0, right? This thing is not accelerating, so we know that this has to equal that. So therefore, we say that F1 equals T rope. Awesome. Now, hold it. What is F1? It's a kinetic friction, right? Kinetic friction, yeah. So, okay, so F1, so it's, okay, so F1 is mu k top. Oh, all the mu k's are the same. Isn't that nice? Okay, they could have been really rotten, you know. They could have had a different mu k here and a mu k here, but it's all the same, so that's nice. Okay, so F1 is mu k N1, right? Which is just mu k M1G. All right, so now F1 equals T rope, which was mu k M1G. So therefore, we're supposed to find T rope. Well, we got it right there. So plug it in. So T rope, mu k is 0.4. M1 is 1. Isn't that nice? 9.8 meters per second squared. 3.9 newtons. Okay, great. Okay, so that's T rope. We got it. So T rope is 3.9 newtons. All right. Okay, now we've got to figure out A. All right. So, M2. Okay, M2. There's friction, so we want to do the y forces first. So the sum, oh, that's good. So the sum of the y forces is N2 minus M1, minus N1 minus M2G. That equals 0. Now, what do we want? Okay, we're going to have two frictions, right? So which normal do we want? This one or this one? Obviously this one, right? Okay, so we want to solve for N2. So therefore, N2 equals N1 plus M2G. Now, wait a second, but I erased it, sorry. What's N1? Well, just look at it. What's N1? M1G, right? So this is m1g plus m2g, which is just g m1 plus m2. Okay, now does that make sense? I mean, think about it. The surface is exerting a force N2 up, right? Now, doesn't it make sense that this N2 up equals m1g plus m2g? Well, yeah. So I mean, all I'm saying is that it makes perfectly good sense, right? Okay. All right, so that's cool. Now we do the messy one. Sum of the x forces. Okay, so here we go. We have T pull to the right, T pull to the right. We have minus F2 top. That's kinetic friction. We'll have to deal with that in a minute. We have minus F2 bottom. That's kinetic friction. We'll have to deal with that in a minute. And that's it, right? Psh, psh, psh. Yeah. And that equals M2A. All right. Now, okay, now let's do it. Let's see, what is F2 top? Well, F2 top is just this, right? I mean, you know. So F2 top is just F1, which is just T rope. Hey, we already got that. Okay, so F2 top, and again, look, just look at how you connect your little lines here. I wish he wouldn't, well, whatever. Okay, so F1 is equal to F2 top, which is T rope. So F2 top is T rope. All right, now, what is F2 bottom? So F2 bottom is mu k times what? Times N2, right? Right? The kinetic friction here is the coefficient of friction times the normal. So F2 bottom is mu k N2, which is that mess, which is mu k g m1 plus m2. Oh, that's not so bad then. Okay, so therefore, so we have T pull minus T rope minus this mu kg m1 plus m2 equals m2a. All right, so divide by m2. Okay, now we're done because we know what T pull is, 20 newtons. We know what T rope is. We figured it up there. We know the mu k's. We know the masses. We're done. So I promise you, you fill all this. I mean, you plug everything in, you get this. Yeah. So this is a nice problem, I think, because you have so many. You have a kinetic friction here and up there for this object. So make sure you understand this one. Oh, all right. Make sure you understand that one. And again, you have to admit, as soon as you draw the force diagrams, after that, it's not so bad. Just F equals ma, F equals ma, F equals ma. That's all it is. All right, so let's pause for a second. When in doubt, draw a complete pictorial representation. Then draw the force diagrams. And once you have the force diagrams, use F equals ma, and you're done. That's all there is to it. Okay, let's see if I want to do this one or not. Yeah, let's do this one. Okay. All right, let's see. So now look it says, what's the tension in a rope? Well, they don't even say anything about the pulley or the rope, so you've got to make some assumptions. What's the assumption? Well, I mean, we haven't learned how to deal with a massive rope or a massive pulley. So massless rope, massless pulley. And it kind of makes sense because, I mean, look, 60 kilogram person, 100 kilogram block, you know, the mass of the pulley is usually going to be a whole lot less than that. All right? So, what's the tension in the rope? Well, how many objects are there? 2. So let's draw force diagrams for the person and then the block. So here's person. Okay, what are the forces acting on the person? Well, there's, you know, gravity, right? So we'll say M person, G, right? And then there's tension. Oops. Tension. Awesome. Now, let's draw the block. What are the forces acting on the block? Now notice there's a little something here. The person's in the air, so there's no normal force. The block is on the ground, so there's a normal force, right? There's a tension up, there's a normal up, and there's a weight down. So that's the difference, you know? Okay, so I'm going to draw it like this. So there's a normal up, there's tension up, that's an N. And then there's the weight of the block. So M block G. Now, here's the beautiful thing. Massless, frictionless pulley, how do these tensions compare? They're the same. If they weren't the same, you'd have too many variables, you couldn't solve the problem. Okay? So the tensions are the same. So this one, okay. All right, let's do the person. So the sum of the y forces equals, we just use Randy Knight, might as well, right? T minus M person G, and that. Now, notice, is the guy accelerating? No, he's stationary, right? So that equals 0. Woohoo! So therefore, the tension equals M person times G. Well, that's wonderful. Okay, so, all right. So let's do over here, sum of the y forces. Again, it's equal to 0, but let's just write it first. So we have T plus normal equal, minus M block G. That equals 0, right? Okay, so, and, oh, we're done. Oh, so we're done, right? So, all right, so we know the tension, M person G. All right, and then, sorry. So that was part 1. We did that. Then for the normal, we just solved for the normal, right? So the normal equals M block G minus T. Well, we know M block G, we know T, so we're done. Okay? There you go. Wonderful. Well, if you want the numbers, so the tension here, the tension is 588 newtons, and the normal is 392 newtons. So that was a nice one. Only thing you had to just watch out for is there's a normal force. Well, that wasn't so bad. Let's see. Oh my gosh. Let's see. Hold on here. What's that? 15. Yeah, let's do this one. This may be surprising, the answer. I don't know. Okay, in case A, block A is accelerated along a frictionless table by hanging a 10 Newton weight. Case B, block A is accelerated along a frictionless table by a steady 10 Newton force in the spring. Massless string, pulley, massless and frictionless. Okay, here's the question. Is block A's acceleration here? In other words, is this acceleration equal to that, greater than, or less than? Now, I think a lot of people, they would look at that And they would say, well, gee, it's the same, right? You know, just guess, right? Don't analyze, for goodness sakes. Why would you want to do that? Just kidding, right? Just philosophize, you know? Don't philosophize, analyze, okay? So let's just analyze it, okay? And that's why I underline this, you know? When it says prove your answer, that means you have to do the analysis, right? You have to do the force diagrams and solve for the A's. And that's really the way you always want to do it. You never want to just guess or philosophize. You always want to work it out. All right, so let's do it. Okay, so let's do case A. All right, so so we have the block. Oh yeah, I got to be careful, right? Okay, so there's two objects, right? There's this and this. Okay, so for case A, this is the block A, right? Okay, so the force diagram. What are the forces? There's the normal, there's the weight, and there's the tension. So there's the normal, there's the weight, and there's the tension. And, you know, the sum of the x forces equals MA. I gotta label it, right? And that equals tension. Right? Okay. And then there's B, right? I'm going to call this thing B. Or 10, I'll just call it 10 newtons. 10 newtons. All right. What are the forces acting on it? Well, there's the tension pulling it up, and there's a 10 Newton weight, right? That's the weight, 10 newtons. 10 newtons. Okay. All right. And, let's see, hold on. I want this acceleration to be the same as that. I don't want to mess around with minus signs. So for this one, I'm going to use the Randy Knight coordinate system. But for this one, I'm going to use this coordinate system. All right? This makes it easier, you know. So here I have a positive A going that way. Here I have a positive A going that way. Okay? So sum of the Fy, I have, again, 10 is positive, 10 Newton positive, minus tension equals, I'll just say MB, all right, MBA. Okay, MBA. Okay, so there you go. All right, now I want to plug that in here. So I have 10 newtons minus MA. Oh, I got to put this. A. So 10 newtons minus MA AA equals MB AA, right? And then, so put that on the other side. 10 newtons equals AA MA plus MB, right? So divide by that. That equals A, all right? Okay, so I get AA is 10 newtons over MA plus MB, all right? Okay, so this is case A. So case A, I have A acceleration equals 10 newtons divided by the sum of the masses, MA plus MB. All right, okay, 10 newtons over MA plus MB. Perfect. Now let's do the other one. Okay, now let's do case B. All right, same as before, you know. Now, let's see. Let's do A. All right, so force diagram for this. We might be able to just draw one force diagram here. You'll see. Okay, what are the forces acting on block A for case B? Well, we have the normal, we have the weight, we have the tension, right? Now, sum of the x forces equals the tension, right? That's all there is. So therefore that equals ma times ab, right? Okay, so therefore AB is equal to tension over MA. Now, what's the tension? Massless frictionless pulley. What's the tension? 10 newtons. So we have 10 newtons over MA. So I should have put an A up here, sorry. So, what do you notice? So this was case A. Here's our acceleration, 10 newtons over the sum of the masses. For case B, here's our acceleration, 10 newtons over ma. So which one is bigger? So this is obviously larger than that, right? So we have AB is greater than AA. Ta-da! All right? So there you go. Analyze, don't philosophize. Okay, no, I'm not doing that one. Yeah, let's talk about this one. Want to do it? Yeah, we can do it. This is conceptually, this is a very interesting one. This is 49. Where's 49? Okay. Oh boy. Find an expression for the magnitude of the horizontal force F for which M1 does not slip either up or down along the wedge. All surfaces are frictionless. So just think of M2 being a chunk of ice. M1 is a chunk of ice. Now come on, what does M1 want to do? It wants to slide down, right? But what we're saying is if you have the right F force here, this is not going to slide up or down. Okay? So wow, we got to do that one. So what we're saying then, of course, is M1 does not move relative to M2. Okay, now, wow, how can we put that in terms of physics? What equation can we use? Well, remember, F equals ma, right? That's what we're doing all the time. F equals ma. So what's the horizontal acceleration of M1? How does that compare to the horizontal acceleration of M2 if there's no slipping? The same, right? So, I don't know if it's going to help. Well, I do, but let's say I didn't, right? So when you get a problem like this, in my opinion, the best thing is just to start writing things down that are true, right? And maybe it'll help, maybe it won't. But, all right, so for sure, okay, so M1 doesn't move, right? Doesn't move relative to M2. And that basically means what? It means that A1 equals A2, right? I mean, there's a force, right? So this is moving, Okay. All right, so these two objects have the same acceleration in this direction. Okay, but what else? What's the acceleration of this guy in this direction? 0, right? 0. And again, I don't know if this is going to help or not, but it's true, right? So I also know that I've got to put x's here, yeah? I've got to put x's here so I don't get mixed up later on. Okay, I also know that A1y equals 0. Okay, again, I don't know if this is going to help. Well, I do. But, you just write things down that are true and see where it leads you. Okay. Anything else I can say? No. There's really nothing else, right? I don't think there's anything else. Okay. What are you going to do next? I mean, it's certainly not going to be a kinematic problem, right? It's a force problem because you've got A's, and whenever you see A, you think F equals ma, so forces. So what's rule number 1? When in doubt, draw a force diagram. So let's draw the force diagram for M1. Okay, wow, what a mess. Okay, M1. So Okay, now we're gonna tilt it, right? Oh, that was rotten. That just tilted. Good grief. Okay, doing this again. There, pretty bad. All right, what are the forces on M1? M1G, right? M1G. And now wait a second. All right, so the weight is this way, but what's the direction of the normal? What does normal mean? It means perpendicular to the surface. The normal is this way. Okay? So the normal, that's why I drew this line, right? The normal is this way. Okay? So there's my theta. All right? Okay. I mean, here's my theta too, right? All right, anything else? There's no friction. There's the normal. There's the weight. I mean, that's it, right? That's it. Okay, so we know that that is true. So we know that the sum of the y forces equals 0. All right. So what are the y forces? So this is n1. So this is n1 cosine theta, right? So we have n1 cos theta minus m1g. Okay, equals 0. So therefore, n1 cos theta equals m1g. All right, hope that helps, but could do something. Now we'll do the x. Okay, sum of the x's. Well, what is it? It's just n. We're gonna resolve this vector, right? So it's n sine theta. So call it n1. Yeah. So n1 sine theta, and that equals m1a, right? m1a1x to be picky, right? Okay. So all right. So in other words, okay, let me just write over here. n1 sine theta equals m1a1x. All right. Now let's draw the force diagram for M2. Okay, so what are the forces acting on M2? There's the weight. There's a normal force from the surface. But what else is there? Well, M2 is pushing this way on M1, so M1 is pushing that way on M2. All right? So, so if I were to draw this, so this is, I'm just going to call it N1, all right? Okay? N1. And there's my theta. Okay, so let's do it. Sum of the, all right, okay, sum of the x forces equals m2a2x. And what is that? Okay, we're going to resolve this thing, right? To a down piece and a piece like that. So, oh, I forgot my f. Golly, that would have been really bad. Okay, so we have f pointing to the right. We have, let's see, what is this? N, let me draw it like this. N1 sine theta, right? This is N1. This is N1 cos theta. This is N1 sine theta. So the sum of x forces equals F minus N1 sine theta. And that has to equal M2A2x. All right, so therefore, F equals M2A2x plus N1 sine theta. Okay. Wow. Okay, so we're supposed to get an equation for F. All right? And all we know is m2 and m1 in theta. Okay? And so this is not sufficient, okay, because we don't know. I mean, they don't give us a2x, they don't give us n1, so we got to substitute, all right? We've got to do a bunch of substitutions. That's all right. So let's do it. All right, so we have m, let's see, what do we know? Let's see, what do we know? Let's see, hold on a second. Okay, we want to get n1, right? Yeah, all right, so n1 equals m1g over cos theta. All right, so we got that. Now, we got to get something for a2x. We can do it. Yeah, we can do it. Okay, because why? Look at a2x equals a1x, right? Yes. Okay, so a1x equals a2x, which is this n1 sine theta over m1, right? All right, awesome. But what's n1? n1 is m1g. So n1 is m1g over cos theta. But then we have a sine theta. Then we have an m1, right? I'm just plugging n1. Sorry, this. I'm plugging this in here, right? So the m1 cancels. What's sine over cosine tangent? So we get g tan theta. All right, so here we go. So m2, a2, which is g tan theta, plus n1 sine theta. So n1 sine theta, so multiply. So we have m1g sine theta over cos theta. Sine over cosine is tangent. Tangent theta. So we can just write that nicely by saying g tan theta m1 plus m2. There you go. Okay, so look, the only way to solve this, you know, we had to use this fact, these facts, a1x equals a2x, right? Because right here, you know, I had an a2, and I said, I don't know how to get that, but then I remembered that a1 equals a2, right? And we had an a1 right there. So we had to use the fact that a1x equals a2x. We also had to use the fact that a1y equals 0, and we used that to get this. So without these two facts, no way, you know, no way. All right, and again, you know, we had to use Newton's third law, right? Because M2 pushed on M1, but M1 pushed on M2. And so we had, you know, that. Oh, I look at that. I even have it in there. So there you go. There's the force diagrams. And that's it. All right, we're done. Okay, so chapter 7, Newton's third law. We learned how two systems interact, right? If there's a force A on B, there's another force B on A, equal in magnitude, opposite direction. We identified reaction pair, you know, force pairs, right? We used the third law, and we talked about propulsion forces and tension forces. Okay, let's just a little bit of review. Forces always come in pairs. If there's an A on B, there has to be a B on A. Simple as that. Same magnitude, opposite directions. Forces in a force pair never, never, never act on the same object, right? What's the object here? B. What's the object there? A. Forces in a force pair are always the same type of force, both gravity, both normal, both electrical, both magnetic, both who knows what. I don't care about that. And that's it. We're done. Thank you. So that was a long